In this video, our focus is to learn L'Hopital's rule. L'Hopital's rule can be used to evaluate the indeterminate forms of the limits when you have 0 over 0 or infinity form. We can also use it in some other forms where we can express our limit into 0 over 0 form or infinity over infinity form. L'Hopital rule says if f of x and g of x are differentiable on the interval ab except possibly at some fixed point c belonging in ab, and g prime of x is not equal to 0 on ab except possibly at x equals c, and limit x approaches c f of x is 0 and limit x approaches c g of x is 0, then limit x approaches c f prime of x over g prime of x exist, and that limit is going to, so if we have an indeterminate form 0 over 0 form, then we can go ahead and take the derivative of numerator, derivative of denominator, and then evaluate the limit x approaches c at that point. If we still get 0 over 0, we can apply the L'Hopital's rule again, and if we get 0 over 0, we can apply the L'Hopital's rule again. This rule is another tool to evaluate the limits that are indeterminate. We have evaluated those limits graphically, numerically, and analytically earlier. L'Hopital's rule is not related to quotient rule, keep that in mind. So in L'Hopital's rule, if we have a limit that we are trying to evaluate and we come up with the indeterminate form 0 over 0 form, then we will do the derivative of numerator and derivative of denominator and then evaluate the limit x approaches c. You need to practice identifying indeterminate and determinate forms. L'Hopital's rule does not always work. It's a powerful technique, but it's just one of the many techniques that will help you calculate the limits. The rule only applies to 0 over 0 or infinity, or if you can express your limit, your problem in the 0 over 0 form or infinity over infinity form, then we can use the L'Hopital's rule. In some cases, we can apply L'Hopital's rule twice, 3 times, 4 times, as many times as we want to, as long as we keep getting 0 over 0 or infinity over infinity. So here's an example. Earlier in the previous sections, we saw that we could factor the numerator and factor the denominator to evaluate this limit. Now we're going to go ahead and use the L'Hopital's rule. First, I'm going to plug in the 3 in here, and I will get 0 over 0 form. So if I get 0 over 0, that means it's indeterminate. And L'Hopital rule says go ahead and take the derivative of numerator, go ahead and take the derivative of denominator, and then plug x equals 3 in there. 3 times 2 is 6, 6 minus 4 is 2, 3 times 2 is 6 plus 1 is 7. 2/7 is the limit. In the previous chapters, we did go ahead and evaluate this limit by factoring x minus 3, x minus 1 over x plus 4, x minus 3. These cancels, limit x approaches 3, x minus 1 over x plus 4. 3 minus 1 is 2, 3 plus 4 is 7. So you get the same limit using L'Hopital's rule. This is just to show you that we have done these problems in a different technique earlier. You can also evaluate the limit numerically. That would be the last attempt or last thing to try. If nothing else works, then go ahead and use the numerical method to evaluate the limit. Next we have limit x approaches 0, 1 minus cos x over x plus x squared. This limit could also be evaluated using the squeeze theorem or sandwich theorem, but I'm going to go ahead, maybe not, that would be 0. Yeah, that wouldn't work out. So we would be evaluating here using the L'Hopital's rule. Let's first go ahead and plug it in. What's cosine of 0? That's 1, and in the denominator I have 0, so it's a 0 over 0 form. That means L'Hopital rule applies. So you should always write down that you are using L'Hopital rule. In this section, I won't be writing it down with every problem, but you should write it down. This section, we are only focusing on L'Hopital rule. So L'Hopital rule says go ahead and do the derivative of numerator. Derivative of negative cos x will be sin x, and derivative of x is 1 plus 2x. Now when x approaches 0, sin x goes to 0. 1 plus 0, 0 over 1 is 0. So this limit goes to 0. L'Hopital's rule. Next, limit x approaches 0, sin x over x. We have seen this one earlier. We also did it numerically, graphically, and we saw this as a special trig limit. We saw the proof of it, geometric proof of this special trig limit. Now we're going to see if I go ahead and plug a 0 in here, this is a 0 over 0 form. If it's a 0 over 0 form, that means L'Hopital rule applies. L'Hopital rule applies. Limit x goes to 0. Derivative of sin x is cos x. Derivative of x is 1. When x goes to 0, cosine of 0 is 1. So this limit goes to 1. 1 minus cos x. Let's go ahead and do the plug in the x as 0, sine of 0, so this leaves you with 0 over 0 form. LH applies. If the L'Hopital rule applies, L'Hopital rule says go ahead and take the derivative of the numerator. That would be positive sine x. Derivative of denominator is cos x. When x goes to 0, sine of 0 is 0, cosine is 1. 0 divided by 1 is still 0. Limit x approaches 0, 1 minus cos x over x squared. Okay, so if I go ahead and plug x as 0, 1 minus 1 over 0, which is 0 over 0 form, so that means L'Hopital rule applies. L'Hopital rule says limit x approaches 0. Derivative of negative cosine x would be positive sine x. Derivative of x squared is 2x. Now, again, go ahead and plug a 0. I'm going to be having 0 over 0 form again. That means I can use the L'Hopital rule one more time. Limit x approaches 0. Derivative of sine x is cos x. Derivative of 2x is 2. When x goes to 0, cosine x goes to 1. So this limit goes to 1/2. This limit goes to 1/2. Let's see next example. Limit x approaches 0. X squared over e to the power x minus 1. So I'm going to go ahead and plug in the 0 first. 0 over 1 minus 1. E to the power 0 will be 1. That would be the 0 over 0 form. That means L'Hopital rule applies. L'Hopital rule says go ahead and take the derivative of numerator and take the derivative of denominator. And again, if I plug in a 0, e to the power 0 is 1. So 2 times 0 is 0. I think we can stop here. 2 times 0 is 0. E to the power 0 is 1. 0 divided by 1 is 0. So this limit goes to 0. X minus sine x over x to the third. Limit x approaches 0. So we have limit x approaches 0. If I plug in 0 minus sine of 0 is also 0 over 0. 0 over 0 form. So L'Hopital rule applies. I'm going to go ahead and take the derivative of numerator, which is 1 minus cosine x divided by 3x squared. Now let's go ahead and plug in the 0. That would again leave me with 0 over 0, and I'm going to say L'Hopital applies again. Derivative of negative cosine x is positive sine x over 6x, which is 0 over 0 again. So I got to apply L'Hopital rule one more time, which is going to be limit x goes to 0. So limit x goes to 0, sine x over 6x. The derivative of sine x is cos x. Derivative of 6x is 6. And that cosine x goes to 1 when x goes to 0. So 1/6 is the limit in this case. You can see we applied the L'Hopital rule once, twice, 3 times in this case. And it's okay to apply it multiple times in a problem. As long as you have 0 over 0 or infinity over infinity form, L'Hopital rule can be applied. Okay, evaluate this limit. Now we're also looking at one-sided limits. So we can also use the L'Hopital's rule for one-sided limits. Limit x approaches 0, sine x over x squared. Okay, let's first go ahead and see the one-sided limits. Limit x approaches 0 from the right-hand side, sine x over x squared. What is going to happen? So limit x approaches 0 from the right hand side. Derivative of sine x is cos x over 2x, and that is going to be 1 over very small positive number. 1 over very small positive number, which is positive infinity. And if I do the other sided limit, limit x goes to negative infinity, sine x over x squared, that is going to leave me with limit x goes to 0 from the left hand side, cos x over 2x, which is 1 over a very small negative number. Very small negative number. 1 over a very small negative number. 1 over a very small negative number will give me a negative infinity. So from one side I have positive infinity, other side of negative infinity, and we can say this limit does not exist. Next example, L'Hopital's rule applied to the infinity over infinity form. All the problems we saw so far were 0 over 0 form. Now we're going to look at some where we have infinity over infinity form. So limit x approaches c f of x over g of x can be written as limit x approaches c f prime of x over g prime of x. As long as your initial form was 0 over 0 or infinity over infinity. As long as this gives you 0 over 0, infinity over infinity, We can go ahead and take the derivative of numerator, take the derivative of denominator, and then apply the limit x approaching c. So here, x approaches infinity, x squared goes to infinity, e to the power x also goes to infinity. So that means L'Hopital rule applies. And I'm going to go ahead and do the derivative of numerator, 2x, and derivative of e to the power x is e to the power x. And this is again infinity over infinity, so L'Hopital rule applies again. And that leaves me with limit x approaches infinity. I do have a repetition here. I wrote it twice. Limit x approaches infinity, 2 over e to the power x. Okay, so 2 over e to the power x goes to infinity. 2 over a very large number is going to go to 0. 2 over a very large number goes to 0. Next, when I plug in infinity, when x goes to infinity, natural log of x, think about what happens to natural log of x when x goes to infinity. When x is getting really, really large, y value is also getting very, very large. 2 root x, square root of x function also goes to infinity when x gets very, very large. So this is infinity over infinity form. Now I'm going to say LH applies. L'Hopital rule applies. You should always mention that what you're doing, which rule you're using. L'Hopital rule says go ahead and take the derivative of numerator, natural log of x is 1 over x, and take the derivative of denominator, and then simplify here. See what you get. Limit x goes to infinity, 1 over x times square root of x over 1. That is going to leave me with limit x goes to infinity, 1 over square root of x, which is going to be 0. 1 over a very large number will turn out to be equal to 0. 1 over a very large number would be equal to a 0. Number 9, limit x approaches pi over 2 secant x over 1 plus tangent x. Always make sure you are in the radian mode. If you're using your calculator, sine of secant of pi over 2 will be 1 over cosine pi over 2. Cosine pi over 2 is 0. 1 over 0 is very, very large. Same thing, tangent pi over 2 is sine over cosine, and cosine is, that would be sine over cosine. So tangent pi over 2 is sine pi over 2 over cosine pi over 2. Sine pi over 2 over cosine pi over 2. That is going to be 1. Cosine pi over 2 is 0. 1 over a really large number is going to be infinity as well. And x is not pi over 2. X is approaching y over 2. So 1 over 0. A very, 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 very small number. Number getting closer and closer to 0 would be almost infinity. Okay, so if we have infinity over infinity form, we can say L'Hopital rule applies. Limit x approaches pi over 2. What is the derivative of secant x? Derivative of secant x is secant x tangent x over 1. Derivative of 1 is 0. So when we take the derivative of denominator, derivative of tangent x is secant square x. 1 of the secant x we can cancel. Limit x approaches pi over 2, tangent x over secant x. Limit x approaches pi over 2, tangent x is sine x over cosine x. Secant x is 1 over cosine x, or cosine x over 1. So we can cancel out the cosine x. Limit x approaches pi over 2, sine of x. That turns out to be 1. That limit will go to 1. Now we're going to look at some other indeterminate forms that don't look like 0 over 0 or infinity over infinity. We can rearrange them into one of those two forms. There are 5 such cases. The first one is infinity minus infinity. So here, limit x approaches 0, 1 over sine of 0, not sine of 0, but getting something really, x being very close to 0, that would be almost 0. 1 over a really large number is infinity. Same thing, 1 over a very small number. 1 over a very, very small number when x approaches 0. Same thing here. X approaches 0 is very, 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 very small number. That would be infinity minus infinity. And we cannot use L'Hopital rule until we have 0 over 0, infinity minus infinity. So I'm going to try to combine the like fractions here. X minus sine of x. Not the like fractions, but trying to consolidate this into a single fraction. Limit x approaches 0, x minus sine of x over x sine x. Let's see, if I go ahead and plug in the zeros, x is 0, sine of 0 is 0, and the denominator x times sine of 0 is 0, which turns out to be 0 over 0 form. Once I have 0 over 0 form, I can say the L'Hopital rule applies, and that means I can go ahead and take the derivative of numerator and derivative of denominator and see if that gets me somewhere. 1 minus cos x over, in the denominator I have to use a product rule, x times cos x plus sine x times 1. So when x approaches 0, where does the cosine of x go? Cosine of x goes to 1. In the denominator, x is approaching 0 plus sine of 0 goes to 0. So that is 0 over 0 form. One more time, I'm getting 0 over 0 form. So that means I'm going to apply the L'Hopital rule again. LH applies one more time. So limit x goes to 0. Derivative of 1 minus cos x would be positive sine x. Derivative of x cosine x would be x times derivative of cos x is negative sine x plus cos x times 1. Derivative of sine x is cos x. Okay, now let's plug in 0. Sine of 0 is 0 over 0 plus cosine of x is 1. 1 plus 1. I put an extra 1 plus 1. Yeah, 1 plus 1. Yeah. Okay, so 0 over 2 is still 0. So this limit goes to 0. Check out a couple more examples. 0 times infinity form. So we have limit x approaches 0, x times natural log of x. When x goes to 0, I have 0, natural log of x. When x is getting closer and closer to 0, natural log of x is going to negative infinity or infinity. Really large negative number. So it's like 0 times infinity form. And that is not okay. We cannot use L'Hopital's rule until we have something in this shape or form. So I'm going to rewrite it. I'm going to say y is equal to limit x approaches 0, natural log of x over 1 over x. Go ahead and take a look at it. It is totally fine to do that, because if you simplify this complex fraction, you're doing natural log of x divided by 1 over x, natural log of x times x. It's back to what you started with. So we didn't change anything except we rewrote it in a different form, the form that's going to work out in our favor. Now let's see, when x approaches 0, natural log of x goes to infinity or negative infinity, and 1 over x, when x goes to 0, 1 over x will go to infinity. So now it is in infinity over infinity form, and we can go ahead and use the L'Hopital rule. L'Hopital rule applies. L'Hopital rule says that to evaluate the limit, go ahead, do the derivative of numerator, which is 1 over x, and x to the power negative 1 would be negative 1 over x squared. Let us simplify. So limit x goes to 0, 1 over x times negative x squared over 1. Limit x goes to 0. I think we can cancel one of the x's. It turns out to be negative x over 1. When x goes to 0, 0 over 1 is going to go to 0. Okay, another one where we have e raised to the power natural log of some function of x. That's how we're going to rewrite it, because we have 1 to the infinity power. Let's check. So when x goes to 0, this piece goes to 0. So I have 1 raised to the power 1 over 0, which is 1 to the infinity power. It's not exactly 0, but it's approaching 0. So 2x is going to be very, 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 very small as x approaches 0. So 1 over a very, 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 very small number. Grab your calculator, do 1 divided by 0.00001. You're going to get a huge number. So 1 to the power infinity. Now I'm going to say y is equal to limit x approaches 0, 1 plus 4x to the power 1 over 2x. Now to tackle problems like this, we would take natural log on both sides. Limit x approaches 0, natural log of 1 plus 4x, 1 over 2x. We can pull out 1 over 2x in the front. Natural log of 1 plus 4x stays here. So just rewriting it, natural log of y is equal to limit x goes to 0, natural log of 1 plus 4x divided by 2x. Let's see, where does that go? When x goes to 0, natural log of any function will go to infinity or negative infinity. And when x goes to 0, Oh, that is not natural log of 0. That's going to be natural log of 1 plus 0. Natural log of 1 is 0, and I'm going to plug a 0 in the denominator. That will also leave me with 0 over 0 form. So if I have a 0 over 0 form, that means L'Hopital rule applies. L'Hopital rule says, go ahead and take the derivative of the numerator and derivative of denominator. That would be 1 over 1 plus 4x times 4 over 2. Simplifying it, limit x approaches 0, 1 over 4 over 2 times 1 plus 4x. 2 over 1 plus 4 times 0, which is 2 over 1. So this turns out to be 2. The right hand side turns out to be 2. On the left hand side, we have natural log of y is equal to 2. Y turns out to be e to the second power. Y turns out to be e to the second power, and that's going to be our limit in this case. See another example. We have limit x approaches x to the power x when x approaches 0 from the right hand side. Okay, so let y be limit x approaches 0 from the right hand side, x to the power x. Go ahead and take natural log on both sides. Pull out the exponent in the front. Natural log of y is equal to limit x approaches 0, x natural log of x. So now again, I'm going to rewrite the right hand side. Limit x approaches 0 from the right hand side, natural log of x divided by 1 over x. When x is approaching 0 from the right hand side, natural log of x is going to negative infinity. As x is getting closer and closer to 0, the natural log of x is going further down. Natural log of x is getting large negative. And when x approaches 0, 1 over x also going to be infinity. 1 over a very, very small number will be infinity. So this is now infinity over infinity form. We can go ahead and use the L'Hopital rule. I'm only going to touch the right-hand side for now and then take care of the left-hand side. Right-hand side, limit x approaches 0 from the right-hand side. Derivative of natural log of x is 1 over x. And we're going to divide it with derivative of 1 over x, which is x to the power negative 1. Negative 1 over x squared. Limit x approaches 0 from the right hand side, 1 over x times negative x squared. Turns out to be negative x. When x approaches 0 from the right hand side, this is going to equal 0. So we can say natural log of y is equal to 0. Y is equal to e to the power 0, which is 1. So limit in this case is equal to, this limit turns out to be 1. See one more example. This is gonna be the last one. Okay, here's another example. We have, this is the exponent, this is in the exponent, so just rewrite it. It's not times 2 over x, it's the exponent 2 over x. So we have an x goes to infinity, we have infinity over 0 form in here. Again, I'm going to try to rewrite it. I'm going to say y is equal to, whenever we have seen exponent, taking natural log on both sides is very, very helpful because it brings our variable exponent in the front and it makes it coefficient. So limit x approaches infinity, 2 over x natural log of x plus 1. Y, natural log on both sides. Limit x approaches infinity, 2 natural log of x plus 1 over x. See where does this go, if we can apply the L'Hopital's rule or not. When x goes to infinity, where does the natural log of x goes to? Natural log of x also goes to infinity because your y values are getting very, very large. And x also goes to infinity, y is equal to x. It's going to pass through origin. It's going to be a line passing through origin, y is equal to x, the slope is 1. So the x also goes to infinity. When x goes to infinity, this function y is equal to x also goes to infinity. So this is infinity over infinity form. That means we can say L'Hopital rule applies, and L'Hopital rule says go ahead and do the derivative of numerator and derivative of denominator. Derivative of numerator would be 2 times 1 over x plus 1. And derivative of denominator is just 1. We don't even need to write it. Limit x approaches infinity, 2 over x plus 1. When x goes to infinity, 2 over a very, very large number is going to go to 0. So natural log of y is 0. Y turns out to be e to the 0 power, which is 1. So this limit goes to 1 when x gets very, very large, positive infinity. That's all for L'Hopital's rule. Again, a quick reminder that L'Hopital's rule does not have anything to do with the quotient rule. Don't be confused about it. You can use it multiple times. It only applies if you have 0 over 0 or infinity over infinity form, and some other indeterminate forms that you can express in the 0 over 0 or infinity over infinity form. All right, have fun.